The signal-to-noise ratio, or SNR, is a large factor when determining POD. When you are trying to detect very small flaws, or when you're inspecting areas in which there is a lot of background noise, the SNR may be quite low, as you can see here. But what if you can reduce the end part of the equation to give your SNR a boost? I'm going to give you a description of the SNR filter on the 21C. This powerful filter intelligently looks for and reduces the noise in the data without attenuating real signals of interest. You may be asking yourself, well, isn't this just a typical threshold filter? The answer is no. A threshold filter will filter out anything below a certain threshold, even the portion of the signal of interest which is below that threshold. This SNR filter will keep the entire signal of interest without attenuation while minimizing the noise component of the signal. Let's start off with a small notch signal in surface array data. So here's your signal here. And let's say you want to get rid of this baseline noise, but you want to keep the entire signal. So turn it on, and here's my SNR limit. So that's the lowest it goes, and it's in divisions. So it looks like this noise is approaching 1 division. So if I go up, for example, as I approach 1 division, it's going to start getting filtered out. And then you can see there, all the baseline noise is gone, but the signal that you want is still there. So that's the key here. A normal threshold filter would eliminate this entire signal here and only keep this. But this SNR filter actually keeps the entire signal. The SNR filter can be applied to all data, not just surface array data. Next, I'm going to show you a case where I take a small EDM notch, which is about 3/4 of a millimeter in length. I'm going to apply a lot of gain to it, so it spans 50% screen height. Increasing the gain like this to a small signal will increase the signal, but because it's so small, it's also going to increase the noise as well. The screen on the left is with the SNR filter applied, and the screen on the right is with no filter applied. You can see the difference that SNR filter makes just by looking at the noise balls there. As I scan past the notch, you will see it momentarily on the screen. And then here I'm going to pause the recording as the probe is at the edge of the notch. You can see on the left with the SNR filter applied, there's practically no noise in the data. Whereas on the picture on the right with no filter applied, you can definitely see a lot of noise. Bolt hole data is notorious for noise. This noise can come from many sources, such as the motor of the scanner, out around holes, or holes which are not clean. Here's an example of a bolt hole with noise in the data. You can see in the sweep display on the left there is noise highlighted by the blue circle. With SNR filter applied on the image on the right, noise is gone. Most importantly, look at the magnitude of the flaw signal and how it did not change. This is the same data, but now looking at a strip chart view. You can see significant noise on the strip chart on the left and zero noise, once again without flaw signal attenuation on the right. As a reminder, like all filters and functions on the 21C, you can activate this filter while acquiring data, or very importantly, you can do it after acquisition. You can scan your data and apply your filters and other settings after acquisition, as I'm doing here in this demonstration. As you can see, the SNR filter on the MIZ 21C can reduce the N, or noise part of the ratio, without affecting the S, or signal part of the ratio, therefore giving you a better SNR. Now you can increase the POD of the exam, you can look deeper into your data, and make the analysis of your data easier.